Right, it's 12 o'clock. Should we get started? All right, so hi everyone. Welcome to the fourth webinar today around what we call machine learning for property modeling. It will be around some technology that SLB as a company has developed for some years. And we will have a presenter today, Raina, who will talk about the technology. So first of all, we would like to say that this is recording and it will be shared at the end of the session. In terms of the meeting and webinar logistics, you can write in any comments or questions in the chat, and we will store them as we go along, and then we will have a Q&A at the end, where Rania and some of our technical experts will be able to answer these questions. And that's the background logistics. So just a quick background before we start. My name is Tormod Slettmås. I lead the digital subsurface technology from Scandinavia, and we basically cover what is in Petrel domain, and this is where that technology that we'll show today is residing. So a quick background on why you're seeing the machine learning for property modeling today. So essentially in geomodeling and in reservoir modeling, classically today we build a grid, we upscale properties, and we property populate for reservoir simulation. The prerequisite is that you have a good understanding of geostatistics with the advantages and limitations that comes with. But a lot of people find that cumbersome, it's time consuming, it's manual, and it requires special knowledge. And sometimes you still get a limited output. So what we have been looking at from the SLB side is machine learning for 3D property modeling. Full machine learning is hard, and there's a lot of research and tests being done on this. What we have worked on is a concept of combining machine learning and geostatistics. And it's essentially a gridless kind of technology, but the background support is a grid. And today we have introduced it in Petrel. We have worked on it with a number of companies globally and also locally in Norway around what we call Innovation Factory. Some of them have been spearheading this and testing it, especially Impex and some other companies in Norway. And we are happy to introduce some of that technology today. So with that, I think I'll leave it to Rania to introduce herself and the technology.
Yeah, hi. Very warm welcome to everyone. Pleasure to be with you today to create awareness and introduce our new technology for property modeling, which I believe it will change our perspective on how to run the property modeling. My name is Raina Carballares. By background, I'm geoscientist. I've been working for SLB now for more than 13 years. And yeah, so I'll take you through the agenda. So the agenda, I'll touch base on the property modeling challenges that we see nowadays, and then the machine learning itself and how does it work, with some examples of different scenarios with the technology, and we'll open the floor for Q&A at the end. So first, I would like to reiterate what Tormod has just briefly addressed. It's like the challenges that it's like a step back to understand why we develop this technology. It's because traditionally we, geologists and geoscientists, try to accurately build the most try to build the most accurate representation of the subsurface reservoir, and therefore we incorporate as many information that we have to integrate, first to integrate complex multi-domain to build statistic property model that helps us estimate reservoir properties like porosity, permeability away from wells. And the resulted models that we build are very crucial for several reasons, to estimate hydrocarbon in place, to plan new wells, and even for carbon sequestration studies and dynamic flow simulation. Geostatistics nowadays remains the standard technique in the industry to interpolate between wells, using seismic data as a secondary variable if you have, or any other, using algorithms such as kriging and co-kriging, and also to perform simulation to model the textural variation associated with facies, for instance, or porosity, using algorithms such as sequential Gaussian simulation. Although the geostatistic has been proven to be great over the past few years, however, it carries a number of challenges and issues, and I believe some of us have experienced that, as it requires expertise and in-depth knowledge of geostatistics to handle all those associated steps that comes with the geostatistics, like data transformation, data detrending, and variogram modeling, to account for the continuity and the variability of the property. And that can be a lot of the time error prone. So things can get wrong or you can get confused. And also it is very challenging when you have more than one property and you would like to incorporate that into geostatistics. So it will be time consuming to do that, because you will have to go through the geostatistical modeling steps for every facies and for every zones. Of course, it also depends on the complexity of the model, but it's still, you will have to repeat the effort several times through the different facies and zones that you have in the model. And that will take a lot of time. It's really time consuming. That can take weeks and can take months as well. For this all reasons, we developed machine learning for property modeling that combines geostatistical modeling with machine learning. Not just to simplify the workflow for property modeling, but also to accelerate it and making it faster by removing 75% of the labor-intensive geostatistical steps that we do nowadays as a geomodeler when we try to build a model, and also make it efficient, by increasing the productivity with less effort, so you don't have to do repeatable steps, and it will also help you generate more constrained realizations and more predictive models to explore the sweet spots that you have in your data, and also a better quantification of uncertainty. So when you use ML for property modeling, you won't need to interact with the geostatistical modeling per se, like the data analysis we have today in Petrel, where you have to open the data analysis and you have to start doing all this geostatistical modeling. Therefore, there will be no concern for stationarity, data transformation, or any variogram models or trending and detrending, so no daunting parameterization that we nowadays see associated with the geostatistical modeling. And also we have measured those steps of the geostatistics versus modeling with geostatistic versus modeling with ML, and we have see that we remove 75% of the intensive labor workflows, labor task that is associated with the geostatistical modeling workflow. Also, the fact that you can handle more than one property it makes it a lot more efficient. For instance, you can drop in when you use ML, you can use as many properties that you have. So a countless number of the properties you can integrate all at once. It can be several attributes, seismic attribute that you extract. It can be geometrical models, a property, sorry, that you generate from geometrical modeling. So as many as you want, as long as you believe that it contains information about your reservoir, you are free to drop it in at once and run the process. And which we compare with nowadays in Geostat, it's not possible, and it can make it more cumbersome. Try to understand the relationship between the different properties that we believe it contains information that we want to be counted in when we run the property modeling. This will be eliminated by the machine learning property modeling because you can drop it in all at once. Also, since you can add as many of information that into the property modeling, you get to efficiently obtain better constrained and robust simulations that it's based on unbiased prediction of sweet spots, because when running ML for property modeling, you will be generating a suite of 3D outputs that helps you to drive decisions based on unbiased predictions, which will be the basis for the simulation. So in essence, what we implemented is a new algorithm named EMBER, Embedded Model Estimator. In this algorithm, superior geostatistical model are embedded into supervised machine learning random forest. And when you open today in Petrel, that's how the process look like. And today it's also available in Delphi with an additional domain profile subscription, and also on-prem from the 2022 up to today. It's now, if you have the right license, and you will have access to it into Petrel under the property model ribbon. It has no dependencies on Project Explorer or OCDU and cloud. So the input required for machine learning there are key required input, which is the training target, the upscalable data, which even today with the classical approach, and when we model in Petrel, we still need the upscale property from our wells, and a 3D grid. If you have additional properties, what we call training feature, of course, by any means you can drop it in, and it's infinite number of continuous or discrete properties that you have. You can drop it in, and you will be ready to run EMBER. Now, once you run, when you run EMBER, you will be generating a suite of 3D outputs based on two workflows. The first workflow is the estimation workflow, and at this stage, EMBER will be trained based on the prior geostatistical embedded models already into EMBER and the training data that we have introduced, like the upscale training data or any additional training data. And based on that, it will construct and provide a conditional distribution function of all the possible estimation, and then out of those estimations, it will give you the final average estimation that we see in the mean as a mean and uncertainty and probability volume, and also other quantiles that you can generate as well. So these are automatically or computed by default. Those estimators of mean and median and uncertainty will be computed by default, and they form the basis of the second stage, which is the simulation, where you generate equiprobable stochastic realization based on the conditional distribution that they have been already obtained from the estimation. And we will see this in a clearer in a short demo. Before I jump into the demo, I would like to introduce some of the new features that have been added into EMBER in the coming in the PTRL 2023 and 2024. One of them is the intervention. This feature, once it's activated, it will enable you to create more geological constraint scenarios by adding additional geological constraint that can be assigning weight to training feature, meaning that a feature that has been like a seismic attribute for saying, for example, that you have used as a training feature, but yet you would like to add more weight into it during the simulation. And also, if you would like to condition it to a facial simulation model that you have already, and you would like to bias the simulation towards that facial model or any conceptual geological model as well. Now, this intervention feature, you will be able to run it when you are after you have run simulation. So this is it won't be active until you have run some simulations, for example, and you're not really very convinced, and you would like to construct better realizations of simulation based on the facial model you have, or a training feature, acoustic impedance, for instance, or any conceptual geological model that you would like to drop it in. Now in 2024.6, it's possible to even use surface as an intervention and use it as a training feature. Before that, it was not possible, but now from 2024, you can add this. And once you activate the intervention, you will have like a drop-down menu and to decide from which intervention you would like to add, and then you will drop it in. And this intervention also can be done globally at the whole grid, or locally for a particular facies, for instance. And I have some examples that I will share with you to illustrate better what I'm trying to say here. Other very interesting feature that we added is the automated quantitative and qualitative quality checks. So these are now in 2024, when you run any of the workflows of the training, the estimation or simulation or blind well test, it will enable you to compute a QC report where it compiles all the information that you will use to QC your EMBER model, either at the stage of the estimation, for instance. You will see that it will automatically compile for you the plots, the histogram, the cross plots that we traditionally nowadays, we go and we do this QC, right? We try to open cross plots and we try to plot our properties, the upscaled versus the model, and we try to see how is the modeling, or open those histograms and try to see the facies, or sorry, for instance, the porosity for upscaled and not upscaled, and the grid. And it also brings you information, the statistics information that we typically try to also access when we go to the property itself. Right click, we go to the settings, and then we try to QC the statistics. Now, with this automated qualitative and quantitative quality reports, it will be gathered for you automatically. You don't have to go back and forth. In addition to further information that it can be tailored specifically for training or for simulation or for blind well test. This is a close look into the estimation quality report. So here, besides the cross plots and the histograms, you will have a specific parameters that help you QC your estimation. One of them is the fraction of variability unexplained, and this gives you an idea of the fraction of variance of the target property that was not correctly estimated from the training features, which are the training features are referring to the secondary property that you will be using into EMBER. The closer to 0, the better the predictivity. The closer to 1, more naive, means that there is more in your model that has not been correctly predictive from the training feature that has been used. Another key information that helps you QC the estimation is the relative variable importance. All this information, as you see, it will be listed for you in the quality check report for you to investigate. So the relative variable importance, it's scaled from 0 to 1, and it will give you a list ranking all the training variables that have been used to train ML. The higher the relative variable importance, the more influence this training have on the training. It doesn't mean that the other variables that they have that they are below than 1, that they are not important or useless, sorry. It's just that it will be less influential at the whole grid, but it can be more influential and have a greater impact locally in a certain zone. And of course, the QC plots and the cross plots. This is another example of a QC report that you can generate when you running EMBER for blind well test. It will combine all the cross plots for you, and it will also give you the measurement of the root square mean, and this is computed in the background, and it's the closer to 0, the better is the predictivity. And with blind well test, so you perform a quality check excluding a number of wells or one well from the estimation, and then you QC the estimation accordingly based on excluding those wells. So you can QC the predictivity of the blind wells using a well section window with predefined template, and that will also be created automatically. And gathering all this information or automatically gather all information in the QC report. So now if you, before that, I would like to mention as well that EMBER, a property for the machine learning for property modeling, it's fully integrated into further workflows like the volumetric assessment and the uncertainty and optimization workflow. So you can take it downstream further for any other Petrel workflows inside Petrel. So if you allow me now to go to EMBER, just so here, if you just, can you see my screen?
Yep.
Yep. So now I'm in EMBER, in Petrel, sorry. So when you open Petrel, first of all, the data set that I will be using, it's a synthetic data from Colin Daly, who is the mastermind behind this technology. And once you are in Petrel, to access EMBER, it will be under property modeling with this little icon with a little brain, and it's named EMBER. When you click on EMBER, that's how it looks like. That's it. Only this dialog box that you will be interacting with all the time. I'll just put it as a new. I will quickly run a demo for EMBER, but before I would like to take you through the process, the dialog box of EMBER. So in here, where you drop in the training target, which can be the upscale, which is the upscale property for the porosity or the permeability. If you just, sorry for a second. In here, yeah, you drop in the upscale property. In this case, I do have one for porosity. And then we have the training feature there where you drop in all the properties that you would like EMBER to learn from to create a property model. And it's important that, of course, you can introduce or drop in all the discrete, continuous, geometrical properties in here, as long as you believe that it contains information for EMBER to learn from. Because if it doesn't contain information, EMBER will not use it. So, and you will see this in the quality when you see the estimation as well. So here I have a number of properties that I have created. But before that, I would like to highlight that if you have only upscale property, by all means, you can still run the process. It will just tell you that if I click to run here, it will tell me that there is no additional training input selected, and it will be purely or heavily running on the embedded geostatistical models and the geometric grids for coordinates and indices. I would say no. So if this is the minimum that you have, you can still run EMBER. But what happened, because EMBER comes with the embedded geostatistical model into it, the geostatistical embedded models are Kriging models for long range and short range. And we also embedded 6 geometrical models to try to capture any potential trend on the data. And that's what we can see under advanced. These are the geometrical features that we have embedded as well to try to capture the trend. So you don't have to worry about trend or any trend modeling. But of course, it doesn't mean that if you perform trend modeling and you can't count it in, you can drop it in as a training feature as well. So at this stage, if I run EMBER only with the training feature, without training feature, I'm running the estimation. It's not the simulation. To run the simulation at the same time, you have to activate it. But first, I will run the estimation first, and then I'll take you through the simulation. So this is the input here, where you drop in the training target, and if you have additional training properties, which I do have here, a number of them, and I will drop it in. And the next step is the trained distribution output. So by default, these grayed out, the mean and the median and the spread will be generated for you by default. There are other output, of course, that you can define based on your need, or if you like, is a probability of distribution above certain value. For instance, if you would like to see the porosity above a certain value and try to explore any sweet spot for future drilling, for example, you can do it from here. And if you would like to produce any additional quantiles, of course, the moment you check these, it will be produced for you. And then under advanced, here we have the training seed, the training simulation, and these are basically the computational the random computational path of ML. And another 2 extra parameters, which is here, is the blind well that I will come to. I will touch base on it in a minute, and the geometrical features to try to capture. Yeah, they are implemented there, and you have the option to exclude them if you like as well. Now, this is the the QC window or the QC report, make sure that it's also toggled on if you want it to be created automatically. So with this input that I have in, I'm ready to run my estimation or my training. So when I click run, what's happening now is the geostatistical model will at the sample well location will inform ML about the spatial continuity and correlation of the target property in our grid. And at the same time, the machine learning random forest will be constructed with all conditional distribution function, and from this conditional distribution at each cell will compute the estimation mean, median, and spread. So as you see, the first thing it has popped up is the QC report that I can close the process. This is the QC report for my estimation. So here I have information about the training statistics, which are how many cells, the number of cells, and the fraction of the FVU, the fraction of variability unexplained. The closer to 0, the better. Here I have at 0.4, it's fine. And then I have the relative variable importance that show me the global contribution of each of the training variable I have. So here I have the long kriging is the most impact or the most impactful variable I have in my model, followed by the short kriging and then the relative acoustic impedance and so on. So again, it doesn't mean that those that they are below that they are useless or not important. Actually, it is. It just at the global level, maybe they're not so impactful compared to the to kriging long range and kriging short range. So these are also the cross plots. Very interestingly, these cross plots are also dynamic. So by default, for instance, it has cross plotted the mean and the median versus the upscaled, and I can choose to see the cross plot of the mean instead with my upscaled property. Also the histogram, I can also choose to display more of my train distribution. And if I go to the input pane here, so after I run, or the moment you run EMBER, it will automatically by default create a folder under properties in the model pane with structure folder of the train distribution. Remember those grade 1 that will compute for you, it will be dropped in automatically under what we called a train distribution. So this structure of the folder, it will be automatically defined for you. So you don't have to worry, you will see that it's under the property, the grid properties, and it has this little brain icon on the folder. Now, here we have two folders, one for the train distribution, the mean and the estimates. This is how it looks like. And also for the probabilities. But I have also created already a layout for the same run where I can display all the output at once. For the sake of time, it's now popping in. Yeah. So this is my model that I generated earlier. So in here, if I just close the report, what we see is in here we see the median, and here we have the mean, and here we have the uncertainty of the training. These are not the final model. So what happened on the background, because the machine learning will construct 500 decision trees at each cell location of probable prediction, of possible prediction, it will construct conditional distribution function of all possible predictions. We're talking about 500 decision trees at each cell location, and then it will create the estimation or the estimator that we see, the mean, the median. So these are an average, the average of the prediction, the average of the 500 decision trees that has been created at each cell. EMBER will create an average of all this and produce the average mean model that we are looking at the moment, and the median, and the quantification of the uncertainty of the train. These are models that are representing the training. It's a representation of the training model. These are not the models that will be taken further downstream into volumetrics, for instance, and further on. At this stage, you probably can have an idea of if there is any, if you have any trend, for instance. At this stage, it can be captured, and therefore, when you run simulation, it will be incorporated, so you don't have to worry about it afterwards of any captured trend during the estimation. Also, those estimations will be the basis for sampling during simulation. When we go next step for simulation, it will be sampling all these CDF, conditional distribution function, that has been obtained during estimation at each cell to run the simulation. So the simulation afterwards will be constrained by the output of the estimation. Oops, sorry. Now, if we decide to go further for the simulation, you can just simply activate this. And in here, you decide, or you identify how many numbers of stochastic realization you would like to generate. And we have introduced some parameterization for your simulation that allow you to control the characteristics of the texture variability. So here it will impact how the texture, the characteristics on the heterogeneity between the wells will look like. For example, the orientation, the continuity, the aspect ratio, and you can perform the simulation globally. So when we don't activate locally, and in here you start allocating the different fascias and zones, it will be run globally through covering the entire grid. All these parameters will be applied throughout the entire grid. And you notice that when I pushed locally here, and you identify certain fascias, then you will be also able to identify the separate simulation parameters for each fascias based on your geological understanding on what you are expecting to be captured during the modeling. For the time being, I will only run the simulation globally. You see, this is the intervenient or the intervention feature. I cannot activate it at this time because it will only be active, or the impact of the intervention will only be applied on the simulation results, not at the level of the estimation. So now, when I run the simulation, it will run, and you can also create a QC window. And here I also have a layout for the simulation and how it looks like. So in my scenario here, I run the simulation. And when you run the simulation, you will have an additional folder under you will have a defined folder for the simulation where all the simulation output will be also predefined for you in a specific folder inside the EMBER main folder, the EMBER case the EMBER main folder that you first already started with. So here, when you run the simulation, you will notice that besides the train distribution and the probabilities, you will also have a simulated result folder that lists down all the realizations that you have identified into the in EMBER. So for instance, in here, I have we are looking at the first simulation realization on the top, and then that's the second simulation realization, and this is the mean and the median and the quantification of uncertainty from the training. So I can see here that I have already captured at the level of the estimation, I have already captured some of my channels that EMBER has learned from my training target and the other training, and it's been captured through the simulation. And the median and the mean are both average of the conditional distribution. The mean, for example, is the arithmetic average of the conditional distribution function at each cell location, and the mid value is the mid value the mid value of the average of the conditional distribution function from each cell. The uncertainty quantification, it's a quantitative measurement of the uncertainty of my training of the trained model. So when there is high uncertainty, it's telling me that it's hard to predict, versus low uncertainty that it's easier. These areas are easy to predict, therefore there is less uncertainty associated with it, and that could be with reference to easy and difficult, meaning that if there are probably more information that EMBER was able to learn about your fascias, for instance, or about a certain geometries that you have, versus areas where it's been, in case of fluvial, where we have a rapid change, that it was a bit challenging for EMBER to learn from your input data about the geometries, for example. Therefore, it's referring to the training that there is a high uncertainty in here. Maybe you need to add more additional secondary properties, for instance. So this is just quickly to introduce to you the output and what is the meaning of the output from EMBER. And the estimations are the basis for the simulation. So you can see, for instance, here in the simulation case that I have, it has been capturing some of the details and some of the geometries of my channels that I see in my estimation. And of course, if you have a good knowledge of the level of understanding of the geological information that you have, and you are expecting certain features, then you can run as many equiprobable realization of your model as you want to try to capture this, and also introduce the intervention. So here, because I'm using the one that I didn't use run simulation, it's grayed out. But if I choose the one that I ran for simulation, it's activated. The moment it's activated, these are the drop-down menu where it enables you to choose what you would like to introduce as an intervention. If it's a user, if it's an additional feature meaning that it can be any of these that you would like to influence or add more weight into the intervention, because you see a delineated geometries of your channels, for example, and you would like to stress or add more weight into it during simulation. You can choose to additional feature and you will drop it in here. And using additional training feature that will allow you to introduce here a preconditioned facials model that you have, and you would like to bias the simulation to, in addition to the intervention strength that enable you to influence the strength of that property that you have used to intervene. And this will only impact the simulation. It won't impact the data. It won't impact the estimation, because all these intervention, it will run conditional sampling within the envelope that has been already constructed during the estimation. So there will be hardly unrealistic output out of this, because it says, as I said, this is happening when you intervene at this stage. You have run already your estimation. You have already constructed the conditional distribution function, and you run the simulation, yet you're not convinced with the output, and you would like to introduce.
It doesn't say anything different. It just like the same. No, so when Lee approves, might get the email says Lee's approved. Now it's waiting for the next step. Yeah. And,
sorry.
After this call, I'm gonna go talk to Per, just so he's aware that I'm using Per. No. Yeah. First waiting for that, and then just if you need me, I can. No. You're gonna speak.
Can someone unmute?
You can mute, yes.
Yeah. So I'm not sure where did I stop. Just like to give you a concept of the intervention. The intervention, when you apply intervention, you want it won't impact the data. It won't impact the estimation. You are impacting the simulation. And somehow you are creating additional, more constrained geological scenarios based on the simulation. At this stage, when you introduce the intervention, you have already not you, but in the background, the conditional distribution function has already been constructed. The estimation models has been already there. So the envelope has been already constructed. It's just that you're not very satisfied with the simulation, and you would like to see if you introduced more bias towards facias, how the output would look like. So what you actually telling EMBER that I would like to capture those features, but meanwhile preserve and without an honor the variability relationship and the real distribution that in my data that has been obtained from the estimation. And addition to that, you can the intervention strength, it will be applied into the within the same envelope as well, is to kind of get more strength on that feature that you use without creating any realistic output. So that's one of the reasons why, for example, intervention, you cannot use it until you run simulation. We have looked at the QC reports that you can produce to QC the predictivity of your model and the simulation. And it will automatically, as I mentioned, it will compile for you quantitative and qualitative information that it's related to the estimation or related to the simulation. In addition to that, we have the blind well test. The blind well test will enable you to QC the predictivity of your model when excluding those wells out of the estimation and or the simulation. This is a layout of my case that I run with blind test. If I go back to EMBER now. So when you run the blind test, you will drop in one well, or it can be a folder of wells. It can be even a safe search of wells that you have, and it will automatically, when you run it, it will automatically create for you two things. One is a well section window. Second is a predefined template for that well section window, and also you will see an additional, you will see an additional folder for your blind well test that has been performed in EMBER. And with EMBER, with the blind well test, you have option to either to introduce only one or a number of one inside of a folder, as I mentioned earlier. Also at the output, you can create, it will by default create an additional folder for the blind well test, and inside that folder will have, you can decide the option to have separate folder for each well or all together combined together with this option. So if you don't click this option, it will create a separate folder and a separate well section window for your blind well test. And in that blind well test, it will display the mean. Like in this one, this is well 21. I'm displaying the mean, the median, and the upscaled log for porosity and the uncertainty estimation of my training. And you will see, for instance, here, because this synthetic model is divided into the modeling here for using the synthetic is trying to model fluvial zones and also tidal shore phase zones. For the fluvial zones, for instance, I can see that there is high uncertainty. It's introducing high uncertainty, and that could be related to the rapid phases change in my phases in the channelized system, versus more or less uncertainty in areas and zones where I have more of smooth transition for the tidal shore phases. And yeah, there should be consistency. Like in this, it's displaying actually a consistency between the upscale data and the output of my training, even though I excluded these wells from the training. And this is the report as well, what gives you information of or compiled information of cross plots and statistics about the blind well test, like this, the root mean square, which is a measurement, a computed measurement for the differences between the sampled and the estimated value. The lower or the closer to zero, the better or the good is the predictivity of the blind test, the blind well test. I will jump back into the presentation. So how does it work? This algorithm, it combines the geostatistical with the machine learning. So at sample well location, the embedded geostatistical Krieger models, long range and short range, will inform ML about the spatial correlation and continuity of the target property, the upscale property in the scenario, and it will transform it into feature, as you see here, and this is the green is the target, is the training target, and this is the embedded geostat that we don't see and we want it to react. So this is just an illustration to try to give you an idea in the background, what's happening in the background. So geostat will estimate the short and the long correlation of at the upscale well location and transform it into feature for machine learning to learn about the spatial continuity and correlation of the target property, and machine learning will learn from the transformed geostat feature besides the training feature that we have, the additional training feature, the secondary variables that we have already incorporated into the process. Machine learning will learn, will gather information from all this, and at the same time, during estimation, the machine learning random forest with 500 decision trees will provide conditional distribution function at each cell of all possible predictions based on the learned or the captured information from the training feature that consists of the geostat and the additional training and the upscaled well data. And it will construct 500 conditional distribution function at each cell location. So if you have a grid of million, then you can multiply this million per 500 conditional distribution of possible prediction. And from these prediction, it will compute the estimation, mean and median, and the uncertainty distribution of the training. And this works very different from the classical ML, because the classical ML will estimate the mean value from the input data. Here, it's estimating the mean value from a conditional distribution of 500 conditional distribution that represents 500 possible prediction. And from that prediction, it will compute mean and median and spread volume of estimation of training. These trainings, this estimation will be the basis for the simulation. So the simulation, when sampling and generating the simulation, the stochastic realization, the sampling at the simulation stage will be based on the already estimated conditional distribution that has been conducted already or obtained from the estimation stage. We have a public technical publication that dives into detail of the algorithm and how it works. Second thing I would like to take you through is some example with the same synthetic reservoir model data, but a different scenario. So in this example, what we tried, what I'm trying to illustrating is that we've run classical property modeling for porosity, and we built what we call a true porosity using the classical property modeling. And we also rebuilt and recreated this property modeling using EMBER. And now I'm taking you through the results to see how this technology was able to reconstruct the reality, together we'll look at the output of EMBER versus the classical approach for this synthetic model. So what we're looking at here, it's a cross-section of the facious model that was built using the classical approach in Petrel. So it's divided into 12 zones representing two depositional environment, the fluvial dominated zones and tidal shore face zones. It's a flattened section, and this is the porosity distribution. It's a cross-section, flattened cross-section as well from a porosity model that has been built using the classical approach in Petrel. So we can see, for instance, here in the tidal shore face, the porosity distribution is continuous, long, with low contrast, and in the compared to the fluvial zone, it's a little bit challenging. It's displaying more heterogeneity, and it's a little bit also challenging to define any geometries, and also that we are looking at a flat cross section, and because also the facies changes here are very rapidly compared to the tidal shore face, where facies are moving upward, prograding lower towards lower shore face. And we also try to create as much heterogeneity as possible with this synthetic data. So what we've done, we have run two scenarios. We ran the first scenario with 8 wells using EMBER. We modeled the porosity using EMBER with first scenario with 8 wells. The second scenario, we used 36 wells with additional training features that consist of seismic attributes, different seismic attributes that we generated from the synthetic reservoir data set, in addition to other properties like a zone indicator, stratigraphic and distance from fault. It's not necessarily that you have to have a zone indicator for instance, but if you have, you can use it. We just try to capture the variability or the information from the data using different attributes. So for the first case, we introduced the upscaled well data with the training features in one go. And to see the simulation output, the simulation output from the 8 wells, we see that if we look into the estimation, for instance, it's indicating that there is the low color of the estimation. The low color we see is indicating low uncertainty estimation, and the dark color is indicating high uncertainty estimation. And we see that there's less uncertainty estimation in the shore face zone, for instance, where it was possible to capture the porosity distribution, that it's moving, that it's transitioning smoothly in the shore face zones, versus the dark estimation. It's showing high uncertainty, and high uncertainty associated with to predict more, and could be a lot because of the heterogeneity of the zones that we see in the fluvial system here in the porosity model, for instance. And that's what we also see, that the uncertainty estimation has captured as well when we see those dark colors, even though we see some of the lighter color, that it's indicating low uncertainty in areas where it was able to capture nice continuity or trend of the facies in the fluvial dominated zones. So if we look at the plan view for the first case, the 8 wells, what we are looking at, what we see in the middle is the true porosity. Let me put as a pointer. So what we are looking at the middle is the true porosity, and this is a constructed porosity model already. This is one of the attributes I used, is the relative acoustic impedance. And on the right side, we see quantiles from the estimation. And on the left side, we see also the quantiles and the simulation and the probability volume of above 15. So if we see at the simulation, for instance, it was able to capture some of the channels that I see that's in the lower part, which is also being captured by the low acoustic impedance in my attribute. And when I defined a probability volume of above 15, I was also able to capture nicely the channels that I see in my acoustic impedance as well, and even when I've gone through the generated different quantiles. However, I can still see here that there is a channel that was not been captured, even when I try to go to as to generate P10, I can still P90. I can barely still seeing some of my channels on the top. However, when I ran with 36 wells, what happened? If I look now at the simulation, at the estimation, I see that some of the channels that I have on the top on my lower truth model has been captured in my simulation and also in my P70 and even in my P10. And it's the same acoustic impedance, it's the same property, but what we added here is additional wells in that area further on the top. So at the first case, it was a bit difficult for EMBER to capture information about channel in this area because it's not shown in the attribute yet. There is no wells for EMBER to learn from or to capture this information and predict the channels in the lower part. When we placed further wells further on the top, EMBER was able to pick up the nonlinear relationship between the porosity and the acoustic impedance and predict the channels on the top. As you see here, this is a probability volume extracted for higher than 15%, and I was able to see some of my channels that I already see in my truth model. So it's important that in your training data or in the data that you have in you use in EMBER to contain this information, so EMBER can learn from and capture the expected feature that you see in your geology. If it's not in the training data, then it will be challenging for EMBER to predict it for you. This is to compare EMBER versus the classical geostat simulation. So what we'll see at the further right, further left is the true porosity, the porosity model using the classical approach. And here we have the simulation by EMBER and the simulation using the classical Gaussian simulation, the SGS, that has followed the classical workflow of performing geostat per zone and etc. Now the differences between the two, sorry, not differences, but the two in the two model, the two scenarios, the facials model has not been used as a constraint. And what we see here with the classical Gaussian SGS, without a strong constraint like the facials model to constrain to, the variability, the stationarity variability will start to kick off, assuming that the variability of the property is the same everywhere, because it's missing this constraint to constrain the simulation. And if we look at the uncertainty estimation here, it's the light where the low color showing low uncertainty and the high color high uncertainty. It's displaying that there is high uncertainty everywhere, except somehow around the wells where we see that the uncertainty is less, and that's a very typical and from the behavior of the classical geostat, where it tells you that there is low uncertainty around the wells and higher uncertainty away from the wells, when in reality it should be high uncertainty where it's challenging to predict, and low uncertainty where in areas that it's easy to predict. And that's why the uncertainty estimation in EMBER, it's very realistic, because it doesn't mean that if we have a relative acoustic impedance high sometimes, that means that there isn't porosity data in some scenarios. But however, we see in this example that there is, because of the heterogeneity and related to the stationarity, the stationarity variability is kicking off and taking control without the facious constraint. It's indicating that there is here, it's hard to predict. The uncertainty is very high, versus low uncertainty here. It's because it was able to capture the smooth or the continuous trend of a little bit here in the short phase zones, versus the zones where we have channelized packages in the data. Back to the intervention, which the next examples I would show is for the intervention with different variables or options to create more geological scenarios. So when you use additional training feature, here you are adding weight to select a training feature to increase the influence of the simulation. And if you use facious model, then you are biasing the simulation to a facious model without the risk of over training, because the simulation or the sampling will be of the intervention will be within the envelope of your trained data, so it won't be overtrained or create unrealistic realizations. And also the intervention strength there is to either positive or negative, is to define or have a more influence, degree of influence on the feature that you have introduced to intervene. Also, we have the target mean intervention. That's another option that you can also use to intervene. And the target mean offsets will only allow within the P10, P90 range of the ML, so it won't compromise the ML, the training of ML. So it will still maintain the integrity with the ML trained model that has been already established during the estimation. And the user numeric, the user defined numeric that you will introduce there, it will not, or it will be actually constrained to the envelope to prevent any unrealistic or unexpected simulation outcomes. So therefore, you will be always within the envelope of the training and the defined training estimation that has been already established. And this is another scenario where we use the intervention using training feature. What we have on the right is the true porosity with 8 wells. And we are looking at the weighted training in this scenario. We used relative acoustic impedance. And we have a simulation realization of EMBER without intervention. And the last one is with the intervention. So what we see here, that when we intervene using the relative acoustic impedance, we were able to capture more of the channels that we see already in the simulation, but we were able to delineate it better when we run the simulation using the training feature, because we see this channel in the relative acoustic impedance. And when we produce the first realization from EMBER without intervention, we still see it, but not really delineated. And when we introduce the training feature, the acoustic impedance, which has already been used as a training feature, but we kind of added more weight into it, I was able to capture more of those channels, and also yet the high porosity areas at the wells up there where there's the circle is still preserved. So it didn't alter the output. It kind of more stressed on and delineated more the geometrical features of the channel. In another scenario, we used the facials model. So instead here, we conditioned or we intervene with already facials model constrained to the wells. So you may not see the differences. You will still see the same porosity, true porosity model on the left. And then in the middle is the facials model. And then we have the EMBER without intervention, which we see that it's captured some of the channels. And when I emphasized, when I introduced the facials, it's a kind of try to bias the simulation more to capture my channels. And I think it didn't go so much different, but I see more of my channels has been identified. Like here, if we look at this channel here, without the intervention was not really identified, but it has taken it, picked it up from my facials model. Now, you probably get to think like, okay, what's the differences between intervention and the co-simulation? They both work in EMBER. It's different when we use the intervention in EMBER. It's very much different. It's very different from the geostatistical with co-simulation. Why? Because EMBER, it's based on nonlinear, non-parametric machine learning approach that estimates multivariate conditional distribution functions at each cell location from which estimations are obtained. So in here, we have the true porosity, and here we have the EMBER simulation with intervention acoustic impedance, and here we have the simulation using the co-simulation as acoustic impedance, and we see very, very different output. Because the acoustic, when I simulate using co-simulation with the acoustic impedance, like in this scenario, the changes will be global, and it will perform a stationary relationship between the secondary variable that you are using as a co-simulation and the target property. So meaning that it will see if in the acoustic impedance here, it's showing that there is high acoustic impedance, there is low porosity, indicating low porosity, high acoustic impedance, high porosity, and that's particularly will be around the wells, and therefore sometimes we end up with some porosity models where it's showing bull eyes, and this is a classical effect as well when we use this co-simulation. It's because this simulation it's based on what the wells is telling us. That it's telling us that there is high acoustic impedance around the well, and there's low acoustic impedance away from the wells, and therefore also you need to have quite a number of wells to capture this as well. So if I validate the output here from the EMBER versus the one from the classic, I can see, or I can tell the one from EMBER, from the classical, it's showing low porosity prediction. It only counted on that particular stationary relationship between the secondary property and the target property. In EMBER, it has counted on multivariate, the machine learning multivariate approach to capture the information from all the training feature that has been added into the process of property modeling. Yes, so for the additional this is additional enhancement, the target mean and intervention, which I touched based already. What I would like to show with this feature is the scenarios or the examples. So this scenario has been run using the global target mean. So often in our data, and our data set, we can have either overestimated or underestimated porosity that can be due to the number of wells or the location of wells in our data set. So with this feature, you can influence the global mean of the simulation. And this is an example where we have, for instance, the porosity. We look at on the left side, we have the true porosity. And then on the middle, we have EMBER with no intervention. And on the left, we have generated EMBER with intervention using the global target mean. And we kind of influence the mean porosity value of the simulation results to move from 14 to 17%, to try to adjust the porosity that we have in our model, that in this scenario, for example, it was underestimated mean due to the data set. For the same feature, we used different input in this scenario. So here we intervene not just with the mean target, but also with the property. So we introduce as an intervention the facious property condition to the existing wells, and locally we introduced the facious that we would like to influence the mean of it, the silt. And the output of this is in this example. So if we look at the true porosity, we see that we have here indicated the porosity for the silt in our channels. And without intervention, it's really not really probably estimated properly. We don't see it really identified. And when we introduce it, as an intervenient, we were able to improve the porosity values in the silt facies, as you can see here, comparing with intervention locally, without intervention. So you kind of adjusted more the porosity for that particular facies. This is to show you the ability of all the tools and the workflows that you can use to capture the most of your information from your data. So to conclude so far, what we believe in, that this new property modeling approach that we have developed, it has a lot of added value when it comes to improve the accuracy of prediction and also the workflow steps. So you have seen so far that I didn't interact with any geostatistics. The geostatistics are embedded into the machine learning, and also the power of the machine learning in learning from the geostatistics and populating the property and predicting your property. And by having this implementation of the geostatistic with machine learning, we have removed 75% of the manual labor-intensive work that is associated with the geostatistical modeling workflow, the steps of all what involved with the geostatistical modeling. And the number of clicks as well were quite fewer with all these automation of the workflows. We see that you've been I've been able to automatically create all these combined quantitative and qualitative reports without the need to open really different cross-plot window, different histogram window, go and check the statistics of that property. I didn't have to do that. Furthermore, there is also interesting published case studies, and personally what I find a lot of interesting is the one for the pre-salt carbonates. I will encourage you to have a look at this case study, and also the one in Indonesia for complicated fluvial, which is this one, for complicated deltatic fluvial reservoir.